I think it's called a surf. X would be lambda dot, is it lambda, that's real lambda and imaginary of lambda, and this max oig apps. Where is my plot? Oh, okay, it's here. How can I rotate it? Okay. I can't really see anything. Okay, so when my mesh is very dense, surf actually doesn't really work. And let me do a contour. Let me do contour F so that it's filled and it's colorful and it's cool. Okay, so here is let me just x label real yeah, y label imaginary and color bar. Right. So what does this mean? Right. So basically, what it means is that the minimum you see is 1. Okay. Everywhere above 1 means unstable. And let me actually do it a little bit differently. Contour bar, I think I can do it with 100 different levels of color so that I can see a little bit more clearly. Where is my, oh, right, okay, so that's better. And let me color bar. So basically this is 1, and we can see it's here. So midpoint is only stable in a short region on the imaginary axis, right? It's good for proving Euler's formula, right? Because we are solving du dt equal to IU. And as long as my, so here, what is the x-axis here? X-axis, x-axis here is 0, which means the real part of lambda has to be 0. The real part, the imaginary part of lambda has to be between -1 and 1, right? And I want to remind you, this is for delta t equal to 1. If I have delta t equal to 0.1, then the imaginary axis is going to go from what? The stability region is going to go from -10 to 10, right? Okay, so yeah, so this is the very restrictive nature of midpoint. Last time in the end of the last lecture, we used the midpoint for an eigenvalue for lambda that is somewhere here, right? It's minus I and I. So yeah, so if delta t is equal to 1, we would be here. If delta t is equal to 0.1, we're actually looking at somewhere here, right? So, but anyway, it's going to be unstable. The amplification factor here is greater than 1. Okay, we can do the same thing for forward Euler. I mean, it's almost a trivial to do at this point, but we can just copy this and Euler, and instead of plotting this, instead of actually, I don't even need to compute this. We know the value, right? We know 1 plus lambda delta d, delta t. So ABS of 1 plus lambda. So if we run it, and let's actually just copy these 2 lines to here, we would get forward Euler. Oh, lambda ij. Okay, where are we? Yeah, I think it takes a while to plot. Right, so this is forward Euler, and I think I can hold on and contour and make a very thick contour line. If I can just say a vector 1, I don't know if it helps. Hope it does. No, it doesn't do anything. Does that help? it kind of separates the the two regions, right? I mean, we have a region that is stable, another region unstable, right? So basically, we have a unit circle, but not centered at 0. Wait, but that was it's not true. Why is it here? That's interesting. I don't know, like, how do you make a contour of the level? But let's do this. Let's actually close, and instead of doing this, let's actually say the max of 1 and the max x. So basically, we only plot the region in which it is stable, and everything outside would be unstable. How about that? So it's a little bit clearer. Okay, right. So this region is stable. I mean, this is anything less than 0, because we are taking the max, is going to be raised up to 1. And the outside is going to be unstable. So that's forward order, the stability region of forward order. It's a circle, but centered at -1. Again, if delta t is smaller than 1, we are going to be amplifying the unit circle outward. All right. Questions? Yeah.
So on the midpoint method, did that like line of stability, did that go from negative I delta t to positive I delta t?
The stability goes from negative I divided by delta t to positive I divided by delta t. The smaller delta t is, the bigger the stability region is, right? Yeah, because the matrix always depends on lambda times delta t. All right. Any other questions?